Today, once again, a day of solving no differential equations whatsoever. The topic is a special kind of differential equation, which occurs a lot. It's one in which the right-hand side doesn't have any independent variable in it. Now, since I'm going to use as the independent variable t for time, maybe it would be better to write the left-hand side to let you know, since you won't be able to figure out any other way what it is. dy dt we'll write it this time. dy dt is equal to, and the point is that there is no t on the right-hand side. So there's no t. There's a name for such an equation. Now, some people call it time independent. The only problem with that is that sometimes the independent variable isn't time, it's something else. We need a generic word for there being no independent variable on the right-hand side. So the word that's used for that is autonomous. So that means no independent variable on the right-hand side. It's a function of y alone, the dependent variable. Now, your first reaction should be, oh, big deal. If there's no t on the right-hand side, then we can solve this by separating variables. So why is he even talking about it in the first place? So I admit that. We can separate variables, and what I'm going to talk about today is how to get useful information out of the equation about how its solutions look without solving the equation. The reason for wanting to do that is, A, it's fast, it gives you a lot of insight, and the actual solution, I'll illustrate one or two, may, first place, take you quite a while. You may not be able actually to do the integrations to get it required in separation of variables to get an explicit solution, or it might simply not be worth the effort of doing if you only want certain kinds of information about the solution. So the problem is, therefore, to get qualitative information about the solutions without actually solving. Without actually having to solve the equation. Now, to do that, first of all, let's take a quick look at how the direction field to such equation. After all, it's the direction field is our principal tool for getting qualitative information about solutions. So how does the direction field look? Well, think about it just for a second, and you'll see that every horizontal line is an isocline. So the horizontal lines, and what are their equations? This is the t-axis, and here's the y-axis. The horizontal lines have the formula y equal a constant. Oh, let's make it y equals a y0, let's say, for different values of the constant y0. Those are the horizontal lines. And the point is they're isoclines. Why? Well, because along any one of these horizontal lines, I'll draw one in, what are the slopes of the line elements? The slopes are dy dt is equal to f of y0, but that's a constant because there's no t to change as you move in the horizontal direction. The slope is a constant. So if I draw in that isocline, I guess I've forgotten, as our convention, isoclines are in dashed lines, but if you have color, you're allowed to put them in living yellow. Well, I guess I could make them solid in that case. I don't have to make them dashed. then all the line elements, you put them in at will because they will all have, they're all the same, and they have slope, that, f of y0. And similarly down here, they'll have some other slope. This one will have some other slope, whatever, this is the y0, the value of the, and whatever that happens to be. I'll put in one more, that's the x-axis. I can use the x-axis, that's an isocline too. Now, what do you deduce about how the solutions must look? Well, let's draw one solution. Suppose one solution looks like this. Well, that's an integral curve, in other words. It's a solution. Its graph is a solution. Now, because as I slide along, these slope elements stay exactly the same, I can slide this curve along horizontally, and it will still be an integral curve everywhere. So in other words, the integral curves are invariant under translation for an equation of this type. They all look exactly the same, and you get them all by taking one and just pushing it along. Well, that's so simple, it's almost uninteresting, except that these equations occur a lot in practice. They're often hard to integrate directly, and therefore it's important to be able to get information about them. Now, how does one do that? There's one critical idea, and that is the notion of a critical point. These equations have what are called critical points. And what it is very simple. There are three ways of looking at it. A critical point, y0. What does it mean for y0 to be a critical point? It means, another way of saying it is that it should be a zero of the right-hand side. So if I ask you to find the critical points for the equation, what you'll do is solve the equation f of y equals 0. Now, what's interesting about them? Well, for a critical point, what would be the slope of the line element along, if this is at a critical level, if that's a critical point, look at that isocline. What are its slope? What's the slope elements, the slope of the line elements along it? It is 0. And therefore, for these guys, these are, in other words, are solution curves. But let's prove it formally. So there are three ways of saying it. y0 is a critical point. It's a 0 of the right-hand side, or y equals y0 is a solution to the equation. Now, that's perfectly easy to verify. If y0 makes this right-hand side 0, it's certainly also y equals y0 makes the left-hand side 0 because you're differentiating a constant. So the reasoning, if you want reasoning, is proof. Maybe we can make one line out of a proof. To say that it's a solution, what does it mean to say that it's a solution? It means to say that when you plug in this constant function, y0, that dy0 dt is equal to f of y0. Is that true? Yeah, both sides are 0. It's true. Both sides are 0. Of the value 0. Now, y0 is not a number. Well, it is. It's a number on this side, but on this side, what I mean is the constant function whose constant value is y0. This function, and its derivative is 0 because it has slope 0 everywhere. So this guy is a constant function. It has slope 0. This is a number which makes the right-hand side 0. Well, that's nice. So in other words, what we found are, by finding these critical points, solving that equation, we found all the horizontal solutions. But what's so good about those? Surely they must be the least interesting solutions there are. Well, think of how the picture goes. Let's draw in one of those horizontal solutions. So here's a horizontal solution. That's a solution. So this is my y0. That's the height at which it is. And I'm assuming that f of y0 equals 0. So that it's a solution. Now, the significance of that is because it's a solution, in other words, it's an integral curve. Remember what's true about integral curves. Other curves are not allowed to cross them. And therefore, these things are the absolute barriers. So, for example, suppose I have two of them. Here's y0, and let's say here's another one, another constant solution. I want to know what the curves in between those can do. Well, I do know that whatever those red curves do, the other integral curves, they cannot cross this, and they cannot cross that. And you must be able to translate them along each other without ever having two of them intersect. Now, that really limits their behavior. But I'm going to nail it down even more. So other curves can't cross these. Other integral curves can't cross. Can't cross these yellow curves, these yellow lines, these horizontal lines. But I'm going to show you more. And namely, what I'm after is deciding, without solving the equation, what those curves must look like in between. Now, the way to do that is you draw. So if we want to make steps, everybody likes steps, okay. So step one is going to be find these. Find the critical points. And you're going to do that by solving this equation, finding out where it's 0. Once you've done that, you're going to draw the graph of f of y. And the interest is going to be, where is it positive? Where is it negative? You've already found where it's 0. Everywhere else, therefore, it must be either positive or negative. Now, once you found that out, why am I interested in that? Well, because dy dt is equal to f of y, right? That's what the differential equation says. Therefore, if this, for example, is positive, that means this must be positive. It means that y must be increasing. The solution must be increasing. Where it's negative, the solution will be decreasing. And that tells me how it's behaving in between these yellow lines, or on top of them, or on the bottom. Now, at this point, I'm going to stop, I'm going to stop talking generally, and everything else in the rest of the period will be done by examples, which will get increasingly complicated. Not terribly complicated by the end, but let's do one that's super simple to begin with. I'm sorry, I shouldn't say that because some of you may be baffled even by it, because after all, I'm going to be doing the analysis not in the usual way, but by using new ideas. But that's the way you make progress. All right, so let's do our bank account. So Y is money in the bank, in the bank account. R is the interest rate. Let's assume it's a continuous interest rate. All banks nowadays pay interest continuously. The continuous interest rate. So if that's all there is, and money is growing at that, the differential equation says that the rate at which it grows is equal to R, the interest rate, times the principal, the amount that's in the bank at that time. So that's the differential equation that governs that. Now, that's, of course, just the solution is simply an exponential curve, and there's nothing more to say about it. Now, let's make it more interesting. Let's suppose there's a shifty teller in the bank, and your money is being embezzled from your account at a constant rate. So, so let's let W equal, or maybe E, but E has so many other uses in mathematics. W is relatively unused. W is the rate of embezzlement. Thought of as continuous. So every day a little bit of money is sneaked out of your account because you're not paying any attention to it. You're off skiing somewhere and not noticing what's happening to your bank account. So since it's the rate, it's a time rate of embezzlement, I simply subtract it from this. It's not W times Y because the embezzler isn't stealing a certain fraction of your account. It's simply stealing a certain number of dollars every day, the same number of dollars being withdrawn from the account. Okay, now, of course, you could solve this. This separates variables immediately. You get the answer, and there's no problem with that. But let's analyze the behavior of the solutions without solving the equation by using these 2 points. So I want to analyze this equation using the method of critical points. So the first thing I should do is, so here's our equation, is find the critical points. Notice it's an autonomous equation, all right, because there's no t on the right-hand side. Okay, so the critical points, well, that's where ry equals 0, ry minus w equals 0. In other words, there's only one critical point, and it occurs when y is equal to w over r. So that's the only critical point. Now, I want to know what's happening to the solution. So, in other words, if I plot, I can write away, of course, negative values aren't particularly interesting here. There is definitely a horizontal solution, and it has the value. It's at the height w over r. That's a solution. The question is, what do the other solutions look like? Now, watch how I make the analysis, because I'm going to use 2 now. So if this was step 1, then step 2. What do? Well, I'm going to graph f of y. Well, f of y is ry minus w. What does that look like? Okay, so here is the y-axis. Notice the y-axis is going horizontally because what I'm interested in is the graph of this function. So that function, what do I call the other axis? I'm going to use the same terminology that's used on the little visual that describes this, and that's dy. You could call this other axis the f of y axis. That's not a good name for it. You could call it the dy dt axis because it's, so to speak, the other variable. That's not great either, but worst of all would be introducing yet another letter for which we would have no use whatever. So let's think of it. We're plotting now the graph of f of y. F of y is this function, ry minus w. Well, that's a line. It goes, its intercept is down here at w, and so the graph looks like something like this. It's a line. This is the line ry minus w. It has slope r. Well, what am I going to get out of that line? Just exactly this. Just this. What am I interested in about that line? Nothing other than where is it above the axis and where is it below. This function is positive over here, and therefore I'm going to indicate that symbolically, this by putting an arrow here. The meaning of this arrow is that y of t is increasing. See where it's the right-hand side of that last board? Y of t is increasing when f of y is positive. F of y is positive here, and therefore to the right of this point it's increasing. Here, to the left of it, f of y is negative, and therefore over here it's going to be decreasing. What point is this, in fact? Well, that's where it crosses the axis. That's exactly the critical point, w over r. Therefore, what this says is that a solution, once it's bigger than y over r, it increases. And it increases faster and faster because this function is higher and higher, and that represents the rate of change. So in other words, once a solution, let's say a solution starts over here at time 0. So this is the t-axis, and here is the y-axis. So now I'm plotting solutions. If it starts at t equals 0, above this line, that is, starts with the value w over r, which is bigger than 0, bigger than the value bigger than w over r, then it increases and increases faster and faster. If it starts below that, it decreases and decreases faster and faster. Now, in fact, I only have to draw 2 of those because what do all others look like? They're translations. All the other curves look exactly like those. They're just translations of them. This guy, if I start closer, it's still going to decrease. Well, that's supposed to be a translation. I don't know. Maybe it is. So these guys look like that. Let's do just a tiny bit more interpretation of that. Oh, dear. I think I better leave it there because we got harder things to do, and I want to make sure we have time for them. Sorry. Okay. Next example, the logistic equation. Some of you have already solved this in recitation, and some of you haven't. This is a population equation. This is the one that section 7.1 and section 1.7 is most heavily concerned with, this particular equation. The derivation of it is a little vague. So it's an equation which describes how population increases and the 1 minute the population behavior of some population. Let's call it Y is the only thing I know to call anything today, but of course your book uses capital P for population to get you used to different variables. Now, simple, the basic population equation runs dy dt. There's a certain growth rate, let's call it K, Y. So K is what's called the growth rate. It's actually, sometimes it's talked about in terms of birth rate, but it's the net birth rate. It's the number, it's the rate at which people or bacteria or whatever are dying, are being born versus minus the rate at which they're dying. So it's a net birth rate. But let's just call it the growth rate. Now, that's, if this is the equation, we can think of this, if K is constant, that's what's called simple population growth, and you're all familiar with that. Logistical growth allows for a slightly more complex situation. Logistic growth says that calling K a constant is unrealistic because, you know, the Earth is not filled with entirely with people. What stops it from having unlimited growth? Well, the fact that the resources, the food that the organism has to live on gets depleted. And in other words, that the growth rate declines as Y increases. As the population increases, one expects the growth rate to decline because resources are being used up and they're not indefinitely available. Well, in other words, we should replace k by a function with this behavior. What's the simplest function which declines as y increases? The simplest choice, and if you are ignorant about what else to do, stick with the simplest. At least you won't work any harder than you have to, would be to take k equal to the simplest declining function of y there is, which is simply a linear function, a minus by. So if I use that as the choice of the declining growth rate, the new equation is dy dt equals, here's my new k, the y stays the same, so the equation becomes a minus by, the quantity times y, or in other words, ay minus by squared. This equation is what's called the logistic equation. It has many applications, not just to population growth. It's applied to the spread of disease, the spread of a rumor, the spread of many things. Yeah, a couple of pieces of chalk here. Okay, now, those of you who've solved it, actually solved it, know that the solution, the explicit solution, involves, well, you separate variables, but you'll have to use partial fractions. Ugh. I hope you love partial fractions. You're going to need them later in the term, but I can avoid them now by not solving the equation explicitly. And anyway, you get a solution which is, I was going to write on the board for you, but you can look it up in your book. It's unpleasant enough looking to make you feel that there must be an easier way, at least to get the basic information out. Okay, let's see if we can get the basic information out. What are the critical points? Well, this is pretty easy. I want to set the right-hand side equal to 0, so I'm going to solve the equation. I can factor out a y. It's going to be y times a minus by equals 0, and therefore the critical points are where y equals 0, that's 1, and the other factor is when this factor is 0, and that happens when y is equal to a over b. So there are my two critical points. Okay. What does let's start drawing pictures of solutions. Let's put in those right away. Okay, the critical point 0 gives me a solution that looks like this. And the critical point a over b, those are positive numbers, so that's somewhere up here. So those are two solutions, constant solutions. In other words, if the population by dumb luck started at 0, it would stay at 0 for all time. That's not terribly surprising. But it's a little less obvious that if it starts at that magic number a over b, it will also stay at that magic number for all time without moving up or down away from it. Now, the question is, therefore, what happens in between? So for the in-between, I'm going to make that same analysis that I made before, and it's really not very hard. Look, so here is my dy dt axis. I'll call that y prime, okay? And here's the y-axis. So I'm now doing step 2. This was step 1. Okay, the function that I want to graph is this one, ay minus by squared, or in factored form, y times a minus by. Now, this function we know has a 0. It has a 0 here, and it has a 0 at the point a over b. At these two critical points, it has a 0. What is it doing in between? Well, in between, it's a parabola. It's a quadratic function. It's a parabola. Does it go up or does it go down? Well, when y is very large, it's very negative. That means it must be a downward opening parabola, and therefore this curve looks like this. So I'm interested in knowing where is it positive and where is it negative. Well, it's positive here for this range of values of y. Since it's positive there, it will be increasing there. Here it's negative, and therefore it will be decreasing. Here it's negative, and therefore dy dt will be negative also, and therefore the function y will be decreasing here. So how do these other solutions look? Well, we can put them in. I'll put them in white, okay, because I think this has got to last till the end of the term. So how are they doing? They're increasing in between the two curves. They're not allowed to cross the yellow curve, either of these yellow curves, but they're always increasing. Well, if they're always increasing, they must, what starts here and increases, it must, and are not allowed to cross, it must do something like that. This must be a translation of it. In other words, the curves must look like that. Those are supposed to be translations of each other. I know they are, but use your imaginations. What's happening above? So in other words, if I start with a population anywhere bigger than 0 but less than a over b, it increases to asymptotically to the level a over b. What happens if I start above that? Well, then it decreases to it, because this way, for the values of y bigger than a over b, it decreases as time increases. So these guys up here are doing this. And how about the ones below the axis? Well, they have no physical significance, but let's put them in anyway. What are they doing? They are decreasing away from 0. So these guys don't mean anything physically, but mathematically they exist as solutions. They're going down like that. Now, you notice from this picture that that even though both of these are constant solutions, they have dramatically different behavior. This solution, is the one that all other solutions try to approach as time goes to infinity. This one, the solution 0, is repulsive, as it were. Any solution that starts near 0, if it starts at 0, of course it stays there for all time. But if it starts just a little bit above 0, it increases to a over b. This is called a stable solution because everybody tries to get closer and closer to it. This is called, 0 is also a constant solution, but this is an unstable solution. And now, usually, solution is too general a word. I think it's better to call it a stable critical point and an unstable critical point. But of course, it also corresponds to a solution. So critical points are not all the same. Some are stable and some are unstable. And you can see which is which just by looking at this picture. If the arrows point toward them, you've got a stable critical point. If the arrows point away from them, you've got an unstable critical point. Now, there is a third possibility. What if, okay, I think we better address it because otherwise you're going to sit there wondering, hey, what did he do? It could look like, suppose it looked like this. Suppose it were just tangent. So this is the picture of that curve, the pink curve. What would the arrows look like then? Well, what would the arrows look like then? Well, since they're positive, it's always positive. The arrow goes like this, and then on this side, it also goes in the same direction. So is this critical point stable or unstable? It's stable if you approach it from the left. So how do in fact, do the curves, how would the corresponding curves look? Well, there's our long-term solution that corresponds, this corresponds to that point. Let's call this A, and then this will be the value A. If I start below it, I rise to it. If I start above it, I leave it. I increase. So if I start above it, I do this. Well, now that's stable on one side and unstable on the other, and that's indicated by saying it's semi-stable. Brilliant word. Wonder how long it took to think that one up. Semi-stable. Critical point. Stable on one side, unstable on the other, depending whether you start below it or, and of course it could be reversed. If I'd drawn the picture the other way, it could have approached it from the top and left it from below. You get the idea of the behavior. Okay, let's now take, I'm going to soup up this logistic equation just a little bit more. So let's talk about the logistic equation, but I'm going to add to it harvesting, with harvesting. So this is a very late 20th century concept. So we imagine, for example, a bunch of formerly free-range Atlantic salmon penned in a large, one of these huge factory farms off the coast of Maine or someplace. They've made salmon very much cheaper than it used to be, but at a certain cost to the salmon and possibly to our environment. So what happens? Well, the salmon grow and grow and do what salmon do, and they are harvested. That's a word somewhat in the category of ethnic cleansing, in my opinion. But it's you know, it's again a very 20th century word. I think it was Hitler who discovered that all you had to do was call something by a sanitary name, and no matter how horrible it was, good bourgeois people would accept it. Okay, so the harvesting, which means, of course, picking them up and killing them and putting them in cans and stuff like that. Okay, so what's the equation? I'm going to assume that the harvest is at a constant time rate. That corresponds to, in other words, it's not a certain fraction of all the salmon that are being caught each day and canned. It's a certain, the factory has a certain capacity. So, 400 pounds of salmon each day are pulled out and canned. So it's a constant time rate. That means that the equation is now going to be dy dt is equal to, well, salmon grow logistically, ay minus by squared. So that part of the equation is the same, but I need a term to take care of this constant harvesting rate, and that will be h. Let's call it h. Not h times y, then I would be harvesting a certain fraction of all the salmon there, which is not what I'm doing. Okay, our equation. Now, I want to analyze what the critical points of this look like. Now, this is a little more subtle because there's now a new parameter there, and what I want to see is how that varies with the new parameter. The best thing to do is, the thing not to do is make this equal to 0, fiddle around with a quadratic formula, get some massive expression, and then spend the next half hour scratching your head trying to figure out what it means and what information you're supposed to be getting out of it. Draw pictures instead. Draw pictures. If h is 0, that's the smallest harvesting rate I could have. The picture looks like our old one. So if h is 0, the picture looks like, what color did I, okay, pink. Yellow. Yellow is the cheapest, but I can't find it. Okay. Yellow is commercially available. These are precious. All right, purple. Purple if it's okay, huh? Purple. So this is the one, our original one, corresponding to h equals 0. Or in other words, it's the equation ay squared, ay minus by squared. H is 0. Now, if I want to find, I now want to increase the value of h. Well, as I increase the value of h, in other words, harvest more and more, what's happening? Well, I simply lower this function by h. Now, so for example, if I lower h somewhat, it will come to here. So this is some value, ay minus by squared minus h1, let's say. That's this curve. If I lower it a lot, it'll look like this. So ay minus by squared minus h a lot, h20. This doesn't mean anything, too. Now, obviously, there's one interesting value to lower it by. It's the value which would lower it exactly by this amount. Let me put that in special. If I lower it by just that amount, the curve always looks the same. It's just been lowered. I'm going to say this one is, so this one is the same thing, except that I've subtracted h sub m. What is h sub, where is h sub m on the picture? Well, I lowered it by this amount, so this height is h sub m. In other words, if I find the maximum height here, which is easy to do because it's a parabola, and lower it by exactly that amount, I will have lowered it to this point. This will be the critical point. Now, the question is, what's happened to the critical points as I did this? I started with the critical points here and here. As I lower h, the critical point changed to this and that. And now it changed to this one when I got to the purple line. And as I went still further down, there were no critical points. So this curve has no critical points attached to it. What are the corresponding pictures? The corresponding pictures, well, we've already drawn the picture for h equals 0 is drawn already. The pictures that I'm talking about are how the solutions look. How would the solution look like for this one for h1? For h1, the solutions look like, here is a over b, here is a over b, but the critical points aren't at 0 and a over b anymore. They've moved in a little bit. So they are here and here. And otherwise, the solutions look just like they did before, and the analysis is the same. And similarly, if h2 goes very far, if h2 is very large, there are no critical points. h2 large, no critical points. Are the solutions decreasing all the time or increasing? Well, they're always decreasing because the function is always negative. Solutions always go down, always. The interesting one is this last one where I've decreased it just to hm. And what happens there is this certain magic critical point whose value we could calculate. There's one constant solution. So this is when it has the value y. I'm sorry, I'm calculating the solutions now. So y here and t here. So here it's the value, hm is the value by which it has been lowered. So this is the picture for hm. And how do the solutions look? Well, to the right of that, they are decreasing, and to the left, they're also decreasing because this function is always negative. So the solutions look like this. If you start above, and if you start below, they decrease. And of course, they can't get lower than 0 because these are salmon. What is the significance of hm? hm is the maximum rate of harvesting. It's an extremely important number for this industry. It's the maximum rate, time rate, at which you can pull the salmon daily out of the water and can them without what happening? Without the salmon going to zero. As long as you start above and don't harvest at more than this rate, you'll be following these curves. You'll be following these curves, and you'll still have salmon. If you harvest just a little bit more, you'll be on this curve, and it has no critical points, and the salmon in the tank will decrease to zero. Ooh, late.